Greetings, everyone. Time to increase our efficiency in derivatives yet again and get the next big structural rule, the chain rule. This rule is literally in every derivative and antiderivative that we perform in some form or fashion. It's just part of the natural structure of a lot of our functional systems. The chain rule is built off of composition of functions. Now remember, composition of functions is when you have one function plugged into another one. For example, a composition function could be something as simple as the tangent of x squared, right? So that's a composition function when I have one function inside of another one. You'll notice all of the derivatives that we've been doing up to this point have just been straightforward singular functions that are either multiplied or added or divided, some sort of combination like that. Okay, and up until this point we haven't had anything where they've been composed. And now it's time to finish it up. This is the main structural rule for derivatives, and it will tie together everything, and we'll be able to take the derivative of any combination that we run into. With the chain rule, I'll also be able to finish out some of the other family of functions that we haven't done any derivatives of yet, like exponentials, logarithms, and stage 3 of our power rule. Okay, so let's start and take a look at what this chain rule is, since it's so handy dandy, right? Okay, so here's the idea. Remember, we can think of the derivative like a rate of change, right? dy over dx, rise over run, basically. Sort of a loose interpretation and sort of a misnomer the way this thing is sort of treating each of the individual things like individual quantities. In some ways, dy is an individual quantity, and in other ways, dy over dx really, isn't. It just depends on your situation, really. But for what we're doing here, you can sort of think of them as individual pieces. Because look at what this is saying. It's saying that I can have this fraction is equal to this fraction times this fraction. And you're accustomed to reducing fractions. See the dw in top and bottom? It's like I'm wiping them out and I'm getting dy over dx, right? You're supposed to get that feeling out of it. But that's really not totally what the symbols are saying, though. We're talking about derivatives, right? Things that have limits built into them and continuity as a part of the process and all of that. I'm saying that the derivative of y with respect to x can take a middleman to get to its destination, instead of going straight from a change in y to a change in x, or rather a change in x causing a change in y. That's really what the derivative measurement is. A small change in x causing a small change in y. Instead of getting there directly, it's like I'm taking a middleman, right, through w. If there is such a middleman. Well, and that's kind of what happens when you have a composition function. You've got a function inside of a function, and x has to pass through both functions before it can give you the output, right? If I plug in an x, I've got to square that value and also do the tangent. It's like I got to go through a middleman to go from x to y. Okay? So it looks a lot like your fraction multiplication. But there's also the calculus side of this. So let's look at it from a function standpoint. If I take the derivative of a composition, notice g is the input of the f function there, right? If I take the derivative of a composition, then just like with all of the other rules, it's like taking turns. F gets a turn with the derivative, and so does g. But there's an important little twist here. G is supposed to be an input function for f. G is supposed to be inside, composed inside of f. So when f gets his turn, you leave g alone, remember? So g is still inside, but it's inside the derivative function now, right, of f. Then g gets his turn, g prime, and they're multiplied. These two things are multiplied together, much like these rates are right here. I have to multiply these two rates in order to get the overall rate. And that's basically the same thing that this is saying. It's saying that F can change without G changing measurably. And then you multiply by the change in G, and it's the overall change. Okay? Because G is working inside of F. Another analogy that an old professor of mine used to say is it's like a clock, right, or a watch. You have the seconds working inside of the minutes, right? So every time the seconds move and then it causes the minutes to move, you multiply the two rates to get the total amount of change, right? It's the same idea. The seconds is working inside of the minutes, right? Seconds do this while minutes do this, right? So end up multiplying them. Think of it like a conversion in that case. Okay, so the proof behind this. If I have this composition function, I set up my difference quotient. Notice f of g of x plus h, f of g of x, right? And just as this suggests, what I'm going to do is I'm going to bring in a multiplication of some measured differences, right? That's this, g of x plus h minus g of x. And something over itself, it's like multiplying by 1. So I bring in these measured differences, and you should kind of see this coming, right? I know I'm looking for g prime, so I bring in the numerator of the difference quotient for g. And then what do? Since this is multiplication, right, I can multiply in any order. Basically, the h comes over here, and this difference comes over here, and that's all it is. We swap them out, right? The h went over here, and now look at what we have. Very nice and neat. We have the derivative of g. So I can sort of pack that one away. There he is right there, right? Sort of got that part out of the way. Now let's look at what we have over here, though. Right here. I swapped out, and you'll notice I even altered the limit a little bit, okay? It's a step-by-step process so that you can see where I'm going. I started with limit as h goes to 0, and this one still has that because that's all it needs. But I started here, and you'll notice now it says as x plus h goes to x, okay? Which that's really saying the same thing as this. H is going to 0. I just added x to both sides, right? X plus h is going to x. Okay, extra tweak. As long as g is a continuous function, I can make my next step of what I'm about to say. But we already knew g was continuous. Why? Because I can't take g prime here. I can't say that this rule is valid, that it has a derivative, without that also implying that g is a continuous function. That's every one of these rules we've been talking about since the definition of derivative. Remember, continuity and differentiability go hand in hand. They imply each other. So, since I'm saying that I can take the derivative of g, then this limit can be converted into the limit as g of x plus h goes to g of x. Well, look, I was already at x plus h goes to x, so I just took g of both sides, right? I did whatever g is, it's some function. I did it to both sides of that comparison. And it's still true. G is a continuous function, so g of x plus h is going to go to g of x as h goes to 0, right? That's still the same limit all the way down. This limit, and this limit are all saying the same thing. So why am I changing it if they're saying the same thing? Because I need you to see the gear turning, pun intended from before, of what we're building here and how it's still the same exact thing. You'll notice I've been copying this here to here. I haven't changed anything in the actual build here because it's already done. This is already a derivative, and I'm trying to help you realize which derivative it is. Okay? Look at the way they have the subtraction at the bottom, and then I have the f functions at the top. It looks a lot like that other version of the derivative definition. Here, this thing right here, right? But instead of x, I'm using w. So f of w minus f of a over w minus a. As w goes to a, was f prime of a. It was what we used to talk about a derivative at a single point. Well, in this case, that single point, a, is g of x. It's some value. And w is approaching it. That's like letting h go to 0. G of x plus h is the w, approaching that value. Well, look, they're already all in place. There's w, there's a, w, a. Like I said, this is already a derivative. I just needed you to see which one it was. It's whatever f prime of a is. Well, so that's f prime, right? Here's the f function. And then what's a? A is g of x. So this piece right here, this limit, is the same thing as f prime of g of x. And then we already had times g prime. So there's my chain rule. If I do a derivative of a composition, right, through the limit part here, then this is what the derivative should look like in its form. Okay? So two big key factors. Remember what I said. It's like each thing getting a turn with the derivative, just like with the product rule. Okay? Except since g of x was always inside, he still is when it's not his turn. And then just g prime, no more composition after the multiplication there. Okay? The first way that we usually approach this when somebody's learning this is what I call the substitution method. And that's not an original name. I'm just going to use substitution to show you all the middle steps that eventually, the more we practice this, you're going to skip a bunch of these middle steps. But it's important for you to see the gears behind the watch here, okay? So what's going to happen is I'm going to have some sort of composition function, and I'm going to let a single letter, W or U, or some people use Z, whatever. I'm using W. I'm letting W take the place of an entire function here. So you notice W equals g of x. That's letting it take the place of that. So now y equals f of W. What have I done? I've just separated it into two functions instead of one composition function. That's all I've done. I've just separated the composition out. It's still linked though, because W is sort of like your middleman here. Okay? So according to my chain rule, if I'm interested in dy over dx, which I actually am, because look, the original setup was input x, output y. So this is the derivative I'm interested in, dy over dx. But I can use the middleman to get there easier. dy over dw times dw over dx. But dy over dw has this connection. Y is related to w through the function f. So that's really df dw, right? This derivative. And dw is related to x, or I'm sorry, w is related to x through g. So dw dx is really the derivative of g with respect to x. I'm still multiplying them, but look, that's f prime of w times g prime of x, isn't it? But w is what? G of x. So the last step in the substitution after you've done your two derivatives is you plug back in for w, and notice now everything relies on x again. Okay? So that's the step-by-step process for substitution. I split them up, I do the two separate derivatives here and here, and then I resubstitute back in so that it looks more like the original problem. Okay? So let's do an example. I have y equals sine squared of x. And that's a composition because remember, this is shorthand for sine of x all squared, right? So look at it real quick and see if you can decide what's the outside function and what's the inside function. You'll hear that language a lot with chain rule. I have an outside and an inside function, okay? So notice the outside function obviously is the squared, right? Something squared, right? Something squared is the outside function. The inside function is sine of x, okay? So substitution would have me do this. It would have me split it up to say that w would equal sine of x, and now y is equal to w squared, right? Y would be equal to w squared. So if I'm interested in dy dx, that's my derivative of this, right? Then I need to do dy dw times dw dx. Well, dy dw is just 2w, right? Because I'm just going to do the power rule, drop the 2, times dw dx, which is the derivative of sine x cosine x. And then in the last step, like I did here, we substitute back in for what w really is. What is w for real? W is sine x. So I plug that in. I have 2 sine x cosine x. And that is my dy over dx. Okay? So I use the substitution method to take a chain rule derivative of a composition function. Just then. Okay? Let's look at a few more examples. Let's continue by working a couple of more examples with the substitution rule so that you can get used to all of the moving parts. Okay, so f of x is equal to 3x to the 5th plus 2x, all to the 16th power. Let's take a look at this for a second and see if you can recognize the nested, the composition functions, right? Because that's really what the substitution is designed to help you to see, the functions as separate entities, right? Now, also on a side note, if this was 3x to the 5th plus 2x raised to, say, the 2 power, I probably didn't need chain rule for this. I could just multiply it out. I'm trying to make a point to you here by raising this one to the 16th power. It might as well be the 1600th power. This binomial to the 16th power would be too large for me to fit in a couple of lines on this board if I were to multiply it out and try to do the derivatives. Of course, you could do it, but how large does that exponent have to get before it's just too much work for you to sit here and write out all the individual terms and do all the individual derivatives? Not to mention later on, if we ever had to do any solving with the derivatives, you'd want to refactor it back out. This is already in a nicely factored format, and I'd like to try and leave it that way, and the chain rule will facilitate that particular structure. Okay, so let's go through and do the chain rule now by doing a substitution, right? So I'm going to start by recognizing that f is equal to a nested composition here, where the outside function is the 16 power and the inside power inside function is 3x to the 5th plus 2x. So by substitution, I'll say w is 3x to the 5 plus 2x. And I will then say that f is equal to w to the 16th. So notice I didn't say f of x anymore, right? W is the function of x, and f is a function of w. That still means that f is a function of x, but it's now have the middleman, right? F is a function of x because w is a function of x. And that's the way the chain rule works. It's kind of like passing the buck with who's dependent on who, or who's dependent on whom, right? Later on, that's going to become important when we start shifting things all over the place inside of our functions in order to use the chain rule to our advantage. Okay? So now that I have it all split up like this, I'm going to work out the separate derivatives, right? So f prime of x, that's our goal. Don't forget that that's df dx. So what we're really going to do is df dw times dw dx. So df dw is the derivative here, f relating to w. That's just a power rule. 16w to the 15th power, right? Drop and subtract 1. Times dw dx is the derivative here. I've got a couple of pieces added together. Both of them power rules though, right? So I drop the 5 and I'll get 15x to the 4 plus 2, right? Okay, so now let's finish it up. I have f prime of x is equal to 16 times, what is w, right? I want everything in terms of x, so I bring back in what w is. 3x to the 5th plus 2x, all raised to the 15th power, times this derivative here, 15x to the 4th plus 2. And that's in a format that we could certainly leave this particular function here. Okay? If there were something else to factor, of course you could try to do something here, but there's nothing there to factor in this case. But if there were, you could work on those individual pieces. But this is an acceptable format right here. And what I want you to start working towards is recognizing all the moving parts, but without having to write the substitution in between steps. Okay? This is a good way to keep track of everything, but eventually we want to be able to take our derivatives a lot quicker. So you need to be able to go straight from this step to this one, because as far as the moving pieces go, this is not a complicated one. It just had the inside and the outside derivative, both power rules, right? I could have just said drop the 16, right, to the 15th power, and notice that piece is still there. And then he gets a turn, what's his inside derivative, okay? So that's what we're working towards here. Let's do one more by substitution, and then after this, we'll start doing the chain rules by looking at the moving pieces without substituting. Okay, so I have g of x is equal to secant of 4x over x squared plus 1. Now I need you to recognize that not only is this a chain rule, but it also has a quotient rule built in, right? And it matters. Is it a quotient with a chain in it, or is it a chain rule with a quotient in it, right? Those two are completely different things. This is a chain rule with a quotient inside of it. The chain rule is the whole structure, and then look, the quotient is the inside function, right? Outside function is secant of something. Inside function is the 4x over x squared plus 1. So when I do my substitution, right, I'm going to say that w is equal to the inside function. Notice that's pretty much the standing operating order there. I just let w represent the entire inside piece. And then g is going to equal secant of w, right? Because that's where that thing used to be. When I'm doing g prime, I'm going to do dg dx is equal to dg dw times dw dx, right? That's our chain rule. It has the middleman there. So dg dw, that is the derivative of secant of w. What was that derivative of secant again from last lecture? Oh yeah, secant times tangent. Okay, so I have secant of w times tangent of w. That's just the outside derivative, right? That's the outer derivative of just the secant. Notice the w is the same in both, right? Which is representing the inside piece unchanging, right? Now, times dw dx, times, and I'll go ahead and put a parentheses here, because dw dx is going to be a quotient rule. So I've got to do my low d high minus high d low. So low is x squared plus 1. D high is 4 minus high is 4x. D low is 2x, right? Because I'm just doing the derivative of the x squared and the 1, 2x plus 0, all over what's below squared. Square of what's below, right? Okay. So of course I can simplify this numerator a little bit here. Let's see what we end up with. I have 4x squared plus 4 and then minus 8x squared. All right. Okay, so g prime of x, right? That's dg dx, is equal to secant of 4x over x squared plus 1 times tangent of 4x over x squared plus 1 times, I have 4 minus 4x squared over x squared plus 1 quantity squared. And sometimes what some people may prefer to do is actually write this piece in front of the secant so that you're not getting it confused with something that's inside the secant or the tangent, right? Another way is you could put brackets around these pieces. It's just separately multiplied though, right? So this piece could go in the front if you wanted it to. Also, we don't actually have to put the parentheses here if that's bothering you, or if you just want to put a times right here. It's all good, right? This is as far as you'd really want to bring that derivative anyway, right? There's really not a lot of factoring going on, except for up here. I mean, you could do a little bit of factoring. It's not going to do anything except expand it and make it look a little bit more gross. If we were solving, I would go through with that. But at this point, since I'm just finding the derivative, then this is a good display of that, okay? Let's continue to build our skill with chain rule by now trying to do the derivatives without the substituting step. Let's see if we can see the different pieces and then just let the derivatives build themselves with the chain rule itself. Okay? So let's start with a couple of smaller ones here. I've got 5 times tangent of x squared. So the first thing you need to recognize is, where is the composition? Where is the nested function? What's inside function and what's outside function, right? Inside function here is x squared. Outside function is tangent of something, right? The of something is the mentality that the substitution takes care of for you. It's sort of, takes care of that step with the middleman for you. The of something is the thing that doesn't get a turn at the same time as the outside function, right? So I'm going to do the chain rule, which says do the derivative of the outside first, but leave the inside alone, times give the inside his turn, right? So here we go. 5's along for the ride. Y prime, derivative of tangent is secant squared. Leave the inside alone, times derivative of the inside is 2x. Now in this case, what I would want to do is go ahead and simplify a little bit. The 2x can multiply with the 5, and I would say that my derivative y prime is 10x times secant of x squared, or secant squared of x squared. Okay? So that was a chain rule, right? Outside, inside, multiplying them. We did this one in the last lecture. We were talking about how I could convert that into something else using our trig identities. That works really well when it's sine of 2x, but then we also need to think about what happens if it was sine 3x, sine 5x, sine something else, right? We don't always have identities for those. Well, I want to work this one so that you can see it comes out to be the same answer we got the last time. Okay? So outside function is the sine of something. inside function is just the 2x. So if I do y prime here, derivative of sine is cosine, leave the inside alone, times the inside derivative of 2x is 2. Rewriting this into a neater format, I would just put the extra 2 in front, and I would have 2 cosine 2x. A lot less work than when we split it up and did a product rule on that, right? Okay, now let me upgrade you a little bit. This one looks like it requires a quotient rule, right? Well, notice there's no variables in the top, and that's part of the key here. Since there's no variables in the numerator, I can actually work this with just a chain rule, no quotient rule, right? Here's what I do. I rewrite this as 17 times 3x squared plus 8 to the negative 4 power. Now it's just 17 times something to the negative 4, and it's a chain rule because the something on the inside is also an inside function itself. Okay, so dA dx, or a prime of x, whichever way you want to look at it, is going to be the 17 is along for the ride. I'm doing the outside derivative first, so ignore this inside. It's not his turn. He's just going to get copied. But remember, power rule, for even with the negative numbers, we proved it was okay with negative numbers. I can drop times the negative 4 times 3x squared plus 8. Negative 4 minus 1 is negative 5. That's the outside derivative times inside derivative of 3x squared plus 8. Well, I've got 2 times 3 there. That's going to be 6x plus 0. So just the 6x. Alrighty then. Okay, so now that I've gotten it to this step, I need to simplify it some, right? So I'm going to end up multiplying these pieces that are sort of free-floating. And then this piece right here is to the negative 5th power. I'm going to go ahead and rewrite that back in the denominator. I don't have to, right? Let's take a couple of steps and I'll show you. First, 6 times 4 is 24, times 17 is 408, negative. So negative 408x. And then I still have the 3x squared plus 8 to the negative 5. This is one version of the derivative that I could leave it if I so chose to. Or if I wanted to go back to the original format of the function, I could also say something like a prime of x is equal to negative 408x divided by 3x squared plus 8 to the 5th power. Okay? Either one of those last two are completely acceptable depending on your situation, right? This one is ready to go for more derivatives if you want to do a product rule. This one is if you want to go ahead and lay it out and do a quotient rule, because notice I would have to, there's now an x in the numerator if I wanted to go further with another derivative. All right. Here with b of x, I want you to notice that there's actually 3 functions nested together now. 3 functions that are composed. I have the 4th power on everything. I then have the cosine, which is on top of the 9x plus 1. So there's actually 3 nested functions here. So you need to do it like one of those nested Russian doll eggs, right? You need to do one layer at a time, while every time you do the derivative of the current layer you're on, everything inside of that layer stays unchanged. Then it's the next layer's turn, right? And then you leave everything inside unchanged, and then it's the next layer's turn after that. And it keeps going on and on and on. Okay? So let's do it by looking at the layers. The 4th power is on the outside, right? Then the cosine, then the 9x plus 1 is the most inside, because it's inside of the cosine. All right, so b prime of x. The power rule, remember power rule, I'll drop the 4. Then Everything inside of that stays the same. So I still have the cosine, I still have the 9x plus 1, but I drop the 4, I subtract 1, it's now to the 3 power, right? Okay, now the power part is done. Whose turn is it next? It's cosine's turn. Derivative of cosine is times negative sine, and then I leave the 9x plus 1 alone because he's still inside. It's not his turn yet. Now I do another chain rule. Hence that you see that chain, right? They're starting to chain together. The inside derivative now is the 9x plus 1. His derivative is 9. So times 9. Okay? From here, I'll want to consolidate everything I can, sort of just getting all the outside pieces together. I'll say b prime is equal to negative 4 times 9 is 36. And then I've got cosine cubed 9x plus 1 sine 9x plus 1. Like so. Okay? The more you practice noticing the compositions, the nested functions, and then making sure that every time you do one, everything on the inside stays the same until it's their turn, right? Make sure you're practicing that logical structure step by step by step, and then just writing it out. And you can get through these derivatives much faster than writing out all those substitutions. Can you imagine if you had like 5 nested functions and then trying to substitute each and every one of them? It would fill up an entire page, and it would be pointless to do that. Practice seeing the structures, okay? Practice is the key. And then writing them out one step at a time first. Then worry about simplification afterwards. All right, now we move on to an exciting step, and that is finally stage 3 of our power rule. We've been seeing how this power rule is handy with a lot of the different things that we've been dealing with. If it's polynomials with positive powers, or if it's things that are fractions in the denominators, we can use negative powers. Now we upgrade it even further so that it can handle fraction powers. The power rule is still the same. If you have some number, right, on a variable, the derivative is going to be you drop the number and you subtract 1 from the power. Okay? So notice what we're doing now is we're upgrading that n to being able to be any rational number, which is positive and negative. Okay? But rational numbers include all the fractions. The only possible upgrade from this would be all real numbers, which would include the irrationals. Okay? To do a proof of that one requires something much further down the line in our repertoire, and we typically don't need to go much past this, because a lot of our functions are either going to be positive powers, negative powers, or fraction powers, right? So I know you've been thinking to yourself, when are we going to talk about derivatives of radicals, square roots, third roots, fourth roots, so on and so on? That's what this is. You can convert any radical, the r root of something, into a fraction power. In this case, it's 1 over r. If it happens to be a power and a root, right, in that case, it's n over r. Either way, the same thing. The power rule allows me to convert it into a fraction power. To do the derivative, I simply drop the power and subtract 1, like I do with any other power rule. Okay? Now that we have the chain rule, I can actually go through and we can talk about why this works using a sneaky method is what I call it, and employing the chain rule to find a derivative a roundabout way. Okay? So I'm going to build off of the power rule that we already know and love, but what I'm going to do first is employ something that actually we're going to use again in a later section. It's called the inverse method. Okay? So here's what we do. I have y equals the r root of x. Don't forget that what that means is y to the r equals x, right? If I raise both sides to the r power, then what I get is y to the r equals x, or by definition of what an r root is, y to the r power would have to give me the x back. Here's what I do now. I take a derivative of both sides, d dx. You can do that. Derivative is an action that you do, and if I'm in the situation where I have this equation, I can do the derivative to both sides. In this case, I'm doing it with respect to x. So the right-hand side is very easy. D dx, derivative with respect to x of x, is just 1. Over here, y to the r is a power rule. Y is a variable, r is a number. However, y is not the variable in question of x. So wouldn't, earlier in the history of what we've been talking about, you'd say, well, since it's not an x, the derivative is 0 because it's constant. No. Y is related to x, right? Y is still dependent on x. So I can't say that the derivative is 0 here. Instead, it becomes a chain rule. It's kind of like y has been turned into a sort of middleman here, but he's got a function on the outside of him, the r power. So I do that derivative. I drop the r power, and I have r minus 1 where I leave the y alone. And then times the derivative of y, he gets his turn. That's chain rule, right? Outside derivative, inside derivative. That's the chain rule right here. Well, what's y prime? I don't know. We got to figure it out. But the chain rule still says that the derivative of this is this multiplication, nonetheless. All right, fine. Then now that we're in an equation, solve for y prime. I'm going to divide the ry to the r minus 1 to the other side, and then it looks like this. I take the y to the r minus 1 into the numerator, and all that does is change the signs on the exponent, right? If I move something up, it puts a negative on the power. And instead of r minus 1, now it's 1 minus r. And I have that 1 over r just kind of by itself, right? I just move the y up and out. But what is y? Y is equal to x to the 1 over r power, right? So I substitute it. X to the 1 over r power raised to the 1 minus r power. If I ever have a power raised to another power, I multiply them. So that gives me x to the 1 minus r over r. And this can be simplified right here. 1 minus r over r, I can simplify by doing 1 over r minus r over r, like this, right? And what is this? R over r is 1, so what I get is exactly what the rule is stating there. I have 1 over r times x to the 1 over r minus 1. Okay? So the power rule works for fraction exponents. And that's exciting because that's all of the radicals you could ever imagine. On top of that, it's exactly the same argument with a slight bit of a ramp up on the algebra with the exponents, but the result is the same and for the same reason. Okay? I can do a chain rule when I do the derivative here, and the only difference is instead of x, I have x to the n power. And what this does is it says anytime I have a radical on top of x to a power, it's just x to a fraction where the numerator is not 1 anymore. Power rule still says the same thing. I drop the power n over r, and my new power is n over r minus 1. Okay, so this is stage 3. This is the ramped up power rule. You can use any number as a power and do the derivative of it the same way. Drop the power, subtract 1 from the new exponent to get the new exponent, right? Let's try a few examples. Straightforward one, right? We probably even did this one or one very similar to it way back at the beginning before we were even doing the rules here, right? The derivative of just the square root function. Well, what I do is I write this as x to the 1/2 power, because this is the second root of x to the 1. So it's the 1 over 2 power. It's always power over root. Okay? So then that's just a power rule. I have a variable to a number power. My derivative, f prime, is just where I drop the 1/2 and I do x to the 1/2 minus 1. But of course, 1/2 minus 1, what you'd rather do is instead of minus 1, you'd probably rather do 2 over 2. That will make the subtraction a little bit easier. And so now I have 1 minus 2. And what I end up with is 1/2 x to the negative 1/2. Now, you could leave it like that, but also don't forget there are other ways of writing these things. So I could use the negative power to drop it into the bottom, like this, which of course we already know x to the 1/2 is the square root. So this is 1 over 2 square root of x. Okay, so those last three are all viable ways of writing this derivative. But here is the, pun intended, the power of the power rule. I can do it on positive exponents for normal polynomials. I can do it on negative exponents for rational functions, things that are in fractions. And I can do it on rational powers, which are radical functions. Okay? That power rule covers all of the main function families that you see first and for most of your algebra courses. The only separate rules that we've learned beyond that are the trig ones, right? And then the structures, product, quotient, and now chain, right? So that power rule extends a lot of different families here. Here, look, another example. I want to do the derivative of the 7th root of x to the 4th times sine x. Important to note, the sign is not under the radical. So it's two functions and they're multiplied. Oh, that's a power rule. But before we do it, I need to write this as x to a number power. So I'll put an equals here. Notice it's equals because I have not done any calculus. This is x to the 4 over 7 power. Power over root, like a tree, roots at the bottom, times sine x. That makes this a product rule. So I will then perform it. G prime of x. Remember, product rule is each of them get a turn with the derivative while the other's left alone. So derivative of x to the 4/7 is 4/7 x to the 4/7 minus 1. That's 4/7 minus 7/7. Right? That's what I'm going to be doing. So that gives me negative 3/7. And then I leave the sine x alone. Plus, leave x to the 4/7 alone, times derivative of sine x is cosine x. Okay? Now, one thing that you tend to be able to do on these is you can factor out powers of x. So here's the thing. Remember, when you're factoring, you always pull the lesser power of x out of the function here, right? So here's what I'm going to do. I'm going to say g prime of x is equal to, and look at your two powers of x here. Which one is the lesser number? This one, right? I can actually factor that out because they have the same base. They both have x. Times, I still have 4/7 times sine x. Plus, now be careful here. I'm factoring out x to the negative 3/7. And remember, when you factor, you're actually subtracting powers out. Like if I have x to the 3, x to the 2, x to the 1, and I factor out x to the 1, each one does a minus 1 as you're factoring it out, right? Because I'm subtracting the power that I'm factoring. Well, here, what's going to happen is when I factor out this x to the 3/7 outside, I'm going to get x to the 4/7 minus negative 3/7. Okay? This is not a derivative. I'm just doing some factoring. It's going to be the power that I have minus the power that I'm subtracting out. So notice that gives me a double negative. 4/7 plus 3/7. is what? 4/7 plus 3/7 is 7/7, which is 1. So notice it gives me x cosine x, like this. Okay? Now these last two steps here, either this g prime right here or this g prime right here, either one of those is completely acceptable depending on your situation, right? One may like to solve this equation better than this equation if I were doing some sort of thing where maybe I was letting the derivative equal to 0 and finding where that is, what x values that is, okay? This equation would be much nicer than this one, for example. Or sometimes it may not be trig functions. It might be big groupings of other things that I'm factoring out. There is going to be a lot of factoring involved when you have chains and products and quotients all starting to mix together. And you need to keep track of doing this kind of chunk GCF factoring. Okay? All right, so one more example of derivatives with chain and radicals, right? Radicals come up quite a bit, so let's practice them some more. Notice this one is a chain rule. I have a radical on top of another function. So they're nested. I have a composition here. But I'm not doing any derivatives with a radical present. I'm going to convert that into a fraction power. So z of x is equal to 9x to the 5th plus 4x to the 1/3 power. All right. So from here, z prime is a chain rule. I'm going to do the outside derivative first. Leave the inside alone. So ignore the inside. The outside function is the 1/3 power. So I drop 1/3, leave the inside alone, and then I do 1/3 minus 1. Right? Times, now do the inside derivative. Now it's his turn. That's going to be 45x to the 4th, because I'm dropping the 5 times 9. 5 minus 1 is 4. Plus, derivative of 4x is 4. Okay? So let's clean this up a little bit. 1/3 minus 1 is 1/3 minus 3/3, which is negative 2/3. Right? Okay, so again, this is an okay format because I don't see anything I can factor here. Or if someone asks you to rewrite this as a more clean fraction, then of course this negative power would make you want to move something down. And here's another possible way of writing that out. I would have the 45x to the 4 plus 4, this, times 1 for the numerator. And then 3, and this is the denominator, to the 2/3, right? And of course, instead of 2/3, you could also write it as the third root with a squared. Regardless, there's several different ways you could see that. But like I said, the first way right there is fine too, depending on what you're doing. Let's finish up this particular lecture doing more practicing chain rule, but mixing it with the product and quotient rules. And we talked about this a little bit already. Earlier we did a chain with a quotient inside of it. Now let's look at some of the other things that can happen, okay? And don't forget, it's like I was saying before, whenever you start having these kind of mixtures, you have to look for opportunities to factor before or after or whatever, usually after. And it helps you simplify what it is later on for a lot of the solving that we end up doing, okay? All right, so on this guy right here, I notice that I've got a product, right? Because I have my multiplication right here. But I also notice that I've got a radical in there, right? So as we were just talking about, if I've got a radical, I'm not going to do any derivatives until I convert that into a fraction power. So let's do that. First things first, my original function f is going to be 3x plus 5 squared times 1 minus 2x to the 1/5 power. Okay? All right. Now it looks like a normal product rule. I've got my two things that are multiplied, and I'm going to do each one of them gets a turn while the other one's left alone. Okay? So f prime, derivative. I'm going to do this derivative first. Notice this is a chain rule because I've got a nested group here. I've got the outside function is squared, the inside function is the 3x plus 5. So I'm going to do the derivative of the squared first, which is to drop the 2. Leave the inside alone. It will be to the 1 power then. So I won't even bother writing the 1 power. Times the inside derivative, which is 3. And then the other guy is left alone. He's still there. Okay? Plus, remember we're doing a product rule. That was his turn. Left this guy alone. Now, he gets left alone. 3x plus 5 squared. And it's his turn to take a derivative. So I drop the 1/5. Leave the inside alone. 1/5 minus 1. That's 1/5 minus 5/5. That's negative 4/5 power on that. Also, this was a chain rule. That's the outside derivative of that piece. The inside derivative is the derivative of 1 minus 2x. So that's times negative 2. All right? Okay. So let's see. What can I do to clean this up now? And I know what you're thinking, why don't we just start multiplying things? But I can't because of the 1/5 power here, right? I can't actually do anything with that. So here's what ends up happening. I look at both of these groupings like this. Here's one big grouping, and here's another big grouping. And I try to group factor as much as I can. I see the objects that they have in common, and I just start pulling things out. Okay? What's the first thing I notice that they both have? A 2. Right? Okay. So I'm going to put a 2 outside. Next, I notice that they both have a 3x plus 5 grouping, and I can only take whatever the lowest power is. So there's a 1 power, and there's a 2 power, so I can only take 1. 3x plus 5. Okay? The 3 is going to have to stay, the 1/5 is going to have to stay, but I notice that they both have a 1 minus 2x grouping. So I'm going to pull one of those out, but be careful. Remember, I can only pull the power of one of these two, and whichever one is the lowest is the one, the least is the one that I have to take. So 1/5 and negative 4/5. Negative 4/5 is the least. So that's the power that I'm actually going to pull out here, the negative 4/5 power. Okay, so that's all the things that they have in common. I'm going to put a big bracket, right, around what's left over. All of this was pulled out. All right. So I pulled the 2, so that's gone. I pulled the 3x plus 5, that's gone. The 3 is still there, right? And then 1 minus 2x to the negative 4/5. 1 minus 2x to the 1/5. Okay, so wait, that means one of these is still there. 1 minus 2x, right? And remember how we handled this before. It's the same way that I'm going to handle this in a minute. Since I'm pulling one of the 3x plus 5s, right? I'm going to pull just one. 2 minus 1 is what I'm going to do with that power. It's the same thing here. To go from here to the new power, I'm going to do 1/5 minus negative 4/5. Because it's the power I have minus what I'm pulling out. Well, what's 1/5 minus 4/5? That ends up being 1/5 plus 4/5, right? Which is just 5/5, or 1. Okay? Plus, that's still part of the main grouping here. 3x plus 5, I took one of them, but that means there's still one left, right? 3x plus 5. I did not take the 1/5, so it's still there. I did take the 1 minus 2x to the negative 4/5. That piece is gone. I did take the 2, but did I take the negative? Nope. So change this. This is going to be negative. Close my grouping there. Okay? All right. So now what I'm going to do is I'm going to just start trying to combine this inside since it looks a lot nicer. I don't have a lot of the exponents in my way. So I'm going to take a side step. All of this is going to stay like it is. And I'm just going to simplify this grouping here. Okay, so let's do that. I can distribute the 3. Okay. Three minus 6x. And I can distribute the negative, and I can distribute the 1/5. So that's going to be negative 3/5 x and minus 1. I suppose I could have also pulled the 1/5 and made it to where I wouldn't have to deal with fractions here. But simple enough, it'll be all right. I've got 3 minus 1, which is going to give me a 2. And then I've got negative 6 minus 3/5. But negative 6 is the same thing as negative 30/5. Like this, right? So I end up with 2 minus 33/5 x. All right. So let's write out the final answer here. My derivative, f prime of x, is 2, 3x plus 5, 1 minus 2x to the negative 4/5, and times, this thing right here was what we simplified, 2 minus 33/5 x. Okay? So yeah, quite messy when you first do your product rule, but with a little bit of practice in our factoring big chunks, I'm able to make it look like something that's been streamlined. All right? And later on when we have to solve, and we're going to have to do a bit of that, where the derivative equals 0, these pieces will be very easy to find solutions to that. All right? Okay. Similar idea with a quotient rule. If I've got things that are set up like chain rules in here, inside of my quotient, then you should be looking out, after you do your quotient rule, for things that you can chunk factor like that. Okay? So here, let's look at this one. It's already in a good format for doing my quotient rule. I don't have to convert any negative powers or radicals. You could do the negative power here, yeah, by moving that up, and then it would become a product rule. I'm not going to do that here. So g prime of x is equal to low d high. So I've got x plus 6 to the 3, that's low. Now derivative of high, well, that's a chain rule, right? The inside and the outside. The outside is the 4th power, the inside is the 2x plus 3. So I drop the 4, leave the inside alone. 4 minus 1 is 3, times, here's the chain rule, times the inside derivative, which is 2, right? Because 2x plus 3. Minus, hang on, times 2, minus high d low. So I've got 2x plus 3 to the 4th times derivative of low is a chain rule also. I'll have to do times 3, x plus 6 3 minus 1 is 2. And then the derivative of the inside, derivative of x plus 6, well, that's just 1. Divide. And then square of what's below. So x plus 6 to the third power squared is just to the 6th power. All right. Now, just like before, the top looks sophisticated, but really they have a lot of these chunks that are similar. So what I'm going to do is I'm going to factor out whatever I can of these big chunks and then simplify, bring together whatever's left over, right? So I notice they both have an x plus 6 chunk, and they both have the 2x plus 3 chunks. This one's got a 3 on the outside, and these have 2s and 4s. So no singular numbers are going to come out. But let's continue here. So I know I can pull an x plus 6, and look at your two powers, 3 and 2. So I can pull out 2 of them. I can also do a 2x plus 3, and I'm noticing a 3 power and a 4 power, so I can pull out 3 of them. And that's it. They don't have anything else in common. So I'll put my big bracket here. And let's see, x plus 6 to the 3, and I took 2 of them, right? So I'm left with an x plus 6 to the 1. 2x plus 3 to the 3, and I took 3 of them, so that piece is gone. But the 4 times 2 is still there, so I have an 8 times that parentheses. Minus 2x plus 3 to the 4, I took 3 of them, so I'm left with a 2x plus 3. The 3 should still be there, so 3 is still there. X plus 6 squared, I took both of them, so that piece is gone, and times 1. All right. So everything else is the same here. Before I start simplifying this inside piece, also note that with this quotient rule going on, I have this multiplication of the x plus 6 squared and a division of x plus 6 to a power. I can actually reduce this. This will reduce completely because there's only 2 of them, and it will leave me with a 4th power here. That should sort of make sense to you, because if you remember earlier, it's kind of like a power rule. I had 3 of them in the denominator, and when you do a derivative, you usually only go down by 1 power. And that's actually what ends up happening, right? I end up with only 4 in the denominator after the reduction. Okay, on the side, let's simplify this piece real quick before we follow on. If I distribute my 8, I have 8x plus 48. And then if I distribute my negative 3, I've got minus 6x minus 9, right? For a grand total of 2x plus 39. All right. So let's write down the finished product, pun intended, right? G prime of x is equal to 2x plus 3 to the third times 2x plus 39, that's this piece simplified, all over x plus 6 to the 4th. And there it is, our simplified quotient derivative. Okay? So I hope all of this huge leaps and lots of algebra haven't scared you off. You need to practice. And I hope all of these examples help you get through that practice and continue practicing your rules and your factoring. Okay? Stay tuned as we grow even more with some other methods of taking derivatives using the rules that we now have.